Hello and welcome to this MCA webinar on Industrial Ethernet Comparison for Motion Control Applications. My name is Carrie Hitchner and I am the Marketing Manager for the Motion Control Association. This webinar will be recorded and a link will be sent to you in the next 24 hours. If you have any questions, please submit them in the chat window of your webinar screen and we will answer questions at the end of the webinar as time permits. If there are any questions that are unanswered, please submit your questions via email. I'd now like to introduce our presenter for today's webinar, Sari Germanos. Sari is the Technology Marketing Manager for the Ethernet POWERLINK Standardization Group. His expertise lies in developing complex, distributed, real-time mechatronic applications. He also has significant experience in applying simulation technologies to improve the efficiency of developing large-scale distributed systems. Lastly, I want to thank our sponsor today, B&R Automation, for supporting this webinar. As a global leader in industrial automation, B&R combines state-of-the-art technology with advanced engineering to provide customers in virtually every industry with complete solutions for machine and process automation, motion control, HMI, and integrated safety technology. With industrial Fieldbus communication standards like POWERLINK and Open Safety, as well as the powerful Automation Studio software development environment, B&R is constantly redefining the future of automation engineering. Now I'd like to hand it over to Sari to begin today's presentation.
Great, thank you very much, Carrie. Hello everyone, this is Sari Germanos. So as Carrie mentioned, I'm responsible for the Ethernet POWERLINK Standardization Group in North America. And so we're going to talk a little bit about industrial networking and what does it mean. So I'm going to start with a couple of videos that illustrate this. So this is an example that was developed at a university in Austria. So you see a very simple example of a guy throwing a ball to a robot. The robot catches the ball in midair. This is a vision-based system, so now as you see the repeat, you'll see a couple of flashes that happen. There's two cameras that are located in the ceiling. Those cameras are smart cameras, and they do a calculation, and they transmit information to the robot. The information is actually transmitted to a central processing unit. This unit then does the trajectory calculation, sends a command to the robot, and then the robot goes to the right place at the right time. This is actually an example of a real-time system. It is real-time because it is time-bounded, and the consequences of missing the deadline means that the robot will not make it to the right place at the right time, and therefore will drop the ball. So it's a simple example, and we'll talk a little bit about the architecture of how that's implemented in a few minutes. I'm going to show you another video, and this is a video taken at an automation trade show. So what you're seeing here again is robots that are moving around. It's another vision-based system. There's a vision camera, and it is looking at balls as they go on the belt, and it is commanding the robots to go, and again the robots happen to go to the right place at the right time and move balls around. So there's a lot of complexity there, and here you see a safety thing going on. The door opens, the hand is inserted, the system slows down to a safe motion. Safe motion means that the user cannot get hurt. Once the hand is out again, the system goes back to full speed. Okay, so this is what we're looking at. So in the first example and in the second example, you have a vision camera that is connected to a network. You have a central processing unit that's got some safety features. You have some safety I/O. You have a few robots. You have some sensors. You have some pneumatics. You have some motion. There's a whole bunch of components that are all sitting together on one network, and that's basically what we think of as an ideal network integrated system architecture. The idea is that you have one network that goes through the system. all the components in the system are connected to that network and everything communicates in real time. Okay, so if you think about the classic structure of a machine today, machines today have or can have a variety of field buses. So in this example, you have a PLC. So this is the main controller, and it is connected to a bus which has access control, and then from that access control you have a bunch of axes connected. Then you have another bus that's got more axes and more I/O and a bunch of sensors connected to the I/O. Then you might have another bus that's connected to the safety system, and then you have a bunch of I/O there. So generally people do this for a variety of reasons. One is because some of the components may not be compatible with each other and therefore cannot sit on the same bus. Some of them may be running at different frequencies, and so you have a bus for high frequency control, a bus for lower frequency control, and you're typically limited by bandwidth, and so you have to have all these components, you have all these parallel buses. So these buses are a variety of technologies, and so as you know, eventually a system needs to be maintained in the field. That tends to be very expensive. The diagnostics for a system like that can be quite expensive, and the maintenance will be expensive as well. So if you're in an environment where you have one network that connects all your system gets reduced to something that looks like this. You have a central PLC, then you have a safety PLC, and then you have a bunch of I/O, and you have all the XCs, and everything sits safely on the same network. So now you have one technology. It is very easy to add components to your architecture, and it is very easy to diagnose and maintain because, again, it's one bus and one architecture. So what we're showing here is a bunch of components that are talking to each other remotely. So the concept of remote I/O has been around for a long time. Remote I/O is essential when you're building large machines because you just can't have high-speed I/O cables going over distances of many feet. So systems like RS-485 and CAN have been around for a long time. They are reliable, they're cheap. The problem that we have with these systems is that they have very limited bandwidth. So you can't run things at very high frequency, otherwise you're going to have several buses in order to manage the bandwidth. And then if you want to add imaging and video to your system, you're pretty much out of luck and you're going to have to move on to a better technology. And that's why industrial Ethernet was born. It was primarily to handle larger bandwidth. So people started using Ethernet. Ethernet has been around since 1972. It is a very well understood technology. It is very mature. It's available on all or practically all microprocessors today. They just off the shoot, they have one or two Ethernet interfaces. So it's a technology that is not intimidating to IT, and so people started using Ethernet. The problem with standard Ethernet is that it is based on CSMA CD. So standard Ethernet means that any component sitting on the network can communicate whenever it wants to. And when two components communicate at the same time, you end up with a frame collision. That means that two frames have overwritten each other. So you randomly go back in time and you retransmit. And you keep doing that process. You keep retransmitting until you know that your frame got there without a collision. So the more frames you have on the network, the more subsystems you have on the network, the higher the likelihood of collision, and so your behavior and the time it takes from one frame to get from one component to the next is going to rely on it. Basically, it's a matter of probability. The more components you have, the higher likelihood of collision, and so you have a non-deterministic system. So people introduced the idea of switches to industrial Ethernet. Well, a switch is designed to eliminate the concept of collisions. So a switch will guarantee that component A can speak to component B without any interruption. And if you have several components in your architecture and you need to know who talks to who, so you need to know that in advance, and you have to configure your switch. These are not unmanaged switches that you would go buy at Best Buy. These are switches that you have to configure manually. and control them, knowing in advance what your architecture is going to be like. And then if there are some communications that happen that are unaccounted for, you're going to end up with queues. And if you run out of queue length, your packets are going to get dropped, and then you're going to have to go back and retransmit again. Plus, queues also mean that you're going to have a non-deterministic amount of delay, and again, it depends on the length of the queue. So there are some systems out there, there's many systems out there that are using switched Ethernet today, but switches introduce delays, and they're also quite expensive. So ideally, we would like to have a real-time network that is not dependent on switches. So there's several types of networks out there today. The very well-known ones and the ones that have the larger percentage of the market are Profibus and Ethernet IP. And for the real-time applications, you have some frame-based networks where you might have Circos 3 or EtherCAT. These are token ring-based concepts where you have one frame that goes around from one component to the next in a ring topology. Each component inserts its data in that frame and passes it on to the next guy does the same, etc., until the frame goes back to the master, and then you start all over again. That's basically the description of the protocol in very, very simple terms. And then you have a hybrid network like POWERLINK, and so we're going to talk a little bit about what POWERLINK is and how it works, and why it's around. So let's talk about the ideal network requirements. If I wanted to create a wish list, what are the things I would want to have in a network? So ideally, I'd want to have something that has real-time performance. Again, that means that my performance is bounded. I can guarantee that the data that needs to get there gets there on time. I want a large asynchronous bandwidth because I may not just be transmitting data that's encoder values and drive values and sensor values. I might also want to be transmitting image data in an asynchronous fashion, or I might want to have some video connected. Ideally, why not have that on the same network? And then I might want to do some status updates. So I might want to have a web server, for example, sitting on one of the devices, and it's publishing its status that way. So there are many needs to have asynchronous bandwidth. I'd like to have one network for all automation, so I want to have the ideal network architecture that I showed before. I'd like to have a flexible network topology, which means I don't necessarily want a ring or a star. I might want to have something that's pretty generic, and I want the network to meet my needs instead of having to architect my system based on my network. I'd like to have something that's hot pluggable so that if something goes wrong with a component, I do not have to bring the machine down to replace the component. I'd like to be able to replace the component while the machine is still alive and running. I want to have high availability, so in the manufacturing world, if a machine goes down, it's very costly. So if something goes wrong, you'd like the machine to recover until the service person arrives. I'd like to have something that's immune to electromagnetic noise. And then lastly, I want to have something that's easy to commission, maintain, and diagnose. And maintain and diagnose are really the costly parts. Okay, so let's address the first two network requirements, and I'm going to describe the POWERLINK protocol here. So the way POWERLINK works, the whole point of the design is that we want to have a network that's based on Ethernet. It uses standard Ethernet hardware, but I do not want to have any collisions in my system, and that's how I guarantee that my performance is there. So in POWERLINK, we have the concept of a network master. Let's call it the managing node, MN. And then everything else on the network is a control node. We call it the CN. So you can think of it as a network master and network slaves. So the master is the managing node. Everything else is a control node. And then we will introduce the concept of a cycle. Okay, so what is a cycle? We want components to communicate with each other. What does that mean? It means that they are sharing data. They are sharing, let's think of it as variables. Okay, so I might have an I/O that's an analog value, and I want that value to be shared, and I want that to be shared every cycle. So we define the cycle time as the time taken for every single component on the network to share its value. So that's what we refer to as a cycle. So POWERLINK is a cyclical bus. So the cycle is split into two components. We have the synchronous phase and the asynchronous phase. So during the synchronous phase, that is where all the I/O values are exchanged. So this is, let's call it the real-time data. This is the data that actually, where I might have commands coming from the PLC going to a system. This is where I might have a closed loop control taking place, working with the axes of motion, and then I might have some digital I/O as well. So I want all this data to be shared in real time, and I want that data to be shared every cycle. So I communicate, so the cycle has two components. During the synchronous phase, I share all the real-time stuff. And then during the asynchronous phase, I can do asynchronous communication. So that's when I can do things like standard TCP/IP communications. But again, that communication is going to be scheduled, again guaranteeing that no collisions take place. So here's my cycle time. So the cycle is going to get initiated. Every cycle, the cycle is initiated by the bus master. It puts out something called the start of cycle frame. When the start of cycle frame goes in, it is read by all the components, and everybody synchronizes to that cycle. So here's my start of cycle frame. And then I'm going to start sending requests. I send a request to the first node communicates its data to the second node communicates its data, etc., until I reach the last node, and that communicates its data. And then I put out a start of asynchronous frame. That is when I start my asynchronous communication, and then my asynchronous communication happens. But again, this is all scheduled, which means that I can have a very, very busy network. I can have a network that's 95% utilized, and there are no delays. And that's the beauty of having a network like this with no collisions. So the next thing that I want to talk about is cross-communication, and that's a very, very important feature in POWERLINK. When something like an encoder puts out its value on the bus, that value is going to be seen by every other component on the network. Now, if it's another encoder that doesn't care, it doesn't necessarily listen. But if there's an axis of motion here and it cares about this encoder, and if there's any kind of closed loop control, I might maybe want the PLC to be aware of the encoder count, but I also want some other mechatronic system to also synchronize to that encoder. So when this encoder puts out its value, it's going to be seen by everyone else on the network. And that communication comes from for free, because every time one of these guys puts out its data, it puts it out in broadcast mode, and so that packet goes to everybody on the network. So here you see a start of cycle frame, and then you see the pull requests go to the individual components, and then you see the encoder, for example, reply, and the data goes to everybody on that network. So it is very easy to have fast access synchronization, and you don't need an additional protocol on top of that to do the synchronization. And this is a very, very unique feature in POWERLINK, and it's very powerful. So now let's talk about one single network for all automation. Well, what does that mean? Well, we mentioned that, first of all, we have direct slave-to-slave communication, and that's great. But I want to have a network that might have fast components and slow components running at the same time. So here's an example. You have several cycles here shown. During the first cycle, I have components 1, 2, and 3 communicating, and then I have 4, 5, and 6 communicating, and then I have my asynchronous communication going on as well. Next, I have components 1, 2, and 3 talking again, but now those slots that were occupied by 4, 5, and 6, now 7, 8, and 9 are communicating, and then 10 and 11 are communicating. So 1, 2, and 3 could be fast I/O, or it could be drives, or it could be motors, or encoders. 4, 5, and 6 could be things like pressure sensors or temperature sensors, where those values don't necessarily change every cycle, And so we don't need to communicate every cycle. We can communicate every second cycle, every third cycle, etc. It's up to the network architect to decide how that's going to be implemented. So there's a form of efficiency in POWERLINK called pole response chaining, and this is a very nice feature where after we do the start of cycle frame and everyone synchronizes, I'll send out one pull request that's generic. So instead of sending a pull request to every single component, as I showed in the beginning, I can have a generic pull request that I put out. And then all the nodes will then respond to that one pull request, and they will respond with fixed communication delays. So that way, again, I can guarantee that all those guys can talk, but they talk in the sequence that I defined up front. And again, there are no collisions, but then I'm not wasting any network time for the pull request to take place. And then after that, I can do my asynchronous data. Now, what is also important to know is that I can actually have a mixed mode. So if I have several components that support pull request chaining, but then I have some other components that don't support that feature, I can get all the guys that support the feature to actually communicate first, and then I can go and send out an individual pull request to the last guy or to the last set of guys, and they can respond. So I can actually mix and match both modes within the same cycle. Okay, so flexible network topology and hot pluggability, well, that's very important, so let's take a look at that. And as it turns out, again, I want to remind everyone we're using standard Ethernet, okay? So since I'm using standard Ethernet, hot pluggability is going to come for free. So I'm not doing anything special. This is standard Ethernet hardware. As far as topology goes, so POWERLINK doesn't use switches. So how do we create a star configuration? Well, we actually used old-fashioned hub technology. Why? A lot of people say, well, wait a minute, hubs are dead. How can you use hubs? Well, yes, there aren't as many people making hubs anymore, but hubs are much, much faster than switches. They are much less complex, and they are still very, very cheap, and you can still buy network hubs today for industrial networking. And they are ideal for POWERLINK because I don't need the switch to manage my collisions for me. My protocol's already doing that. So I can use a hub, and then every POWERLINK component also has 2 Ethernet ports. So I'm able to daisy chain my components as well. So here's an example where I have a bit of both. I'm connected to stock topology, and then I'm daisy chaining a bunch of other components. And so all of these guys can see the network at the same time, and this effectively all collapses to one straight network. So let's talk about high availability. Now here's an interesting use of having 2 Ethernet ports. We're going to first start talking about ring redundancy. So in the concept, in this configuration, I have my master. My master is connected to a bunch of components that are daisy chained together. If I take the last component in the daisy chain and I hook it back to the master, I end up with a ring. Now, in this case, the way POWERLINK works is it'll put out, let's say, a pull request, or put out the start of cycle frame, whatever it is putting out, and then it waits and tries to listen to it on the other end. So if it doesn't show up on the other end, then it makes the assumption that one of those cables is broken, at which point it'll put out an error condition, but then it'll start transmitting on both sides. So if one of the cables is broken, the system will continue to run. If 2 cables are broken, you're out of luck. But at least here, if one cable breaks during my operation, I can put out a simple error condition, and then I can continue to run, and then eventually when the operator or the maintenance guy has time, they can come over and they can figure out which cable is broken and it'll replace it. So next, I have something called full medium redundancy. So in an environment that I know is going to be harsh, I might want to have a duplicate network. So I might have 2 concurrent networks running together. And I have every component on the network connected to both of these network connections, and these are connected by a link selector. So the link selectors will sit there and monitor the networks, and the minute the link selector determines that one of the networks has broken, it'll switch over to the other network automatically. And so this switcher over happens without any of the control nodes even knowing, and if it's implemented right, this only takes one cycle to recover. Lastly, I have something called redundant master. Well, the way I've described the POWERLINK protocol so far, the master is responsible for the timing and the communication. So if your master goes down, you have no network. So we can have redundant masters sitting on the network, and they're basically waiting to see what the main master is doing. If they notice that the master goes down, there's a protocol that actually they follow. The redundant master will basically take over the responsibility of the network, and the system continues to function. And again, this failover can happen within one cycle time. So, and POWERLINK supports up to 9 redundant masters. And you can have some very, very highly reliable CPUs as redundant masters. So you end up with a very, very, very safe network and with a high degree of availability. Let's talk a bit about EMC. So here we compare POWERLINK to other real-time networks like possibly EtherCAT or Circos that are token ring based. So as I described before, the token ring concept basically says that one packet starts at the master, goes to the next component, to the next component. Each component puts its data in that frame and passes it along. So if you end up with a noise spike on the network, you're going to lose that frame. If you lose that frame, you effectively lost data from all the devices in that one cycle. So in one shot, you lost everything for that cycle. Whereas with POWERLINK, each component puts its data out in a separate frame. So if one frame goes bad, you only lost data from one component. So if you look at the likelihood of failure, as you add more and more POWERLINK components, that relationship is linear. Whereas if you look at what happens to EtherCAT or Circos, as you add more and more nodes, they become much more susceptible to noise as you add more and more nodes. And so if you're running in an environment like where you have slip rings, POWERLINK tends to be a very, very reliable protocol. So let's look at the last requirement of easy commissioning and maintenance and diagnostics. Now again, because we are using standard Ethernet and because we are using hub technology and not switches, I can see all the data on the network anywhere at any time. So I can take a standard PC running Wireshark, let's say, which is an open source debug tool, and I can see all the sequences of the packets taking place on the network. I can see my pull requests, I can see my pull responses, I can see my start of cycle frames, my start of asynchronous frame, etc., and I can use the Wireshark filters and I can take a look at my whole system sequence on the network. It's a very, very powerful tool. If I want something that's a nanosecond accurate, and if I don't want to rely on my timestamps, there are some network analyzer tools that you can buy that will capture all that data with nanosecond accuracy and put it out again in Wireshark format, and you can grab your data and look at it with the Wireshark application. So it's very, very easy to diagnose a POWERLINK network and see what's going on, and it's very easy to build diagnostics tools that sit on top of POWERLINK and very inexpensive. Okay, so I mentioned before that POWERLINK is standard Ethernet. So I just wanted to illustrate what that means. So we're actually using standard Ethernet hardware. We're using the standard Ethernet frame. So you have your MAC header, you have your MAC source, you have your destination, and this is your POWERLINK ether type. It's OX88AB. That's your POWERLINK ether type, and that's registered. So within the Ethernet payload, that's where the POWERLINK data sits. So within the Ethernet payload, you have your POWERLINK header, your message type, your source, your destination for POWERLINK, and then you have your POWERLINK payload itself. The POWERLINK payload itself has I/O data, drive data, etc. And then you have a section that is reserved for safety packets. So if you need to do safe communication, you can. and the safety packets are actually duplicated, again, for the purpose of redundancy. POWERLINK sits perfectly well within the OSI model. So effectively, POWERLINK is basically a gateway between the IP and the MAC. So in some cases, you're using POWERLINK talks directly to the MAC. In other cases, it allows packets to communicate directly with the MAC, depending on whether you're in the synchronous phase or the asynchronous phase of the cycle. And then the POWERLINK application itself is basically a layer 7 application that sits there. And here you'll see object dictionaries and PDO and SDO. For those of you who are familiar with CANopen, yes, POWERLINK is actually CANopen over Ethernet. So it uses a it's actually the same API, but just with larger frames and a faster cycle time. Speaking of speed, let's talk a little bit about performance. So you can do synchronization in 0.1 microseconds. You can have 100 microsecond cycle times. In fact, you can have cycle times that even run below 100 microseconds. It really depends on the applications. Now, when we talk about automation and we're using off-the-shelf automation components, we're usually talking about drives. Drives usually run at 400 microseconds are the fastest drives that I'm aware of. So it's unusual to talk about anything that's sub 400 microsecond cycle times, but that's not a POWERLINK limitation, that's just the industry limitation. And in a calculated example we have 17 stations, we're running 800 digital I/O signals, 180 analog signals, 24 axes of motion, running at a cycle time of 200 microseconds. So here's an example of a company in Germany called Bruckner. So this company designed a plastic stretching machine. The stretching machine, in fact, this is plastic that, the typical plastic that sits on your laptop screen today. So there's a bunch of linear actuators here that stretch the plastic as it goes through the machine. And in this case, you have 728 axes of motions between linear actuators and linear encoders, and the whole system is running at a 400 microsecond cycle time. Now, I mentioned before, POWERLINK has, you have one network master and then a bunch of control nodes. You can have up to 239 control nodes. Here I'm showing 728 axes of motion, so that basically tells you that there are several POWERLINK networks running concurrently, but they're all synchronized. So again, as I mentioned, POWERLINK is CANopen over Ethernet. So for anyone familiar with the CANopen layer and the CANopen API, it's exactly the same API. You have the same device profiles. The format, the actual XML format of the device profile is a little bit different, but the POWERLINK frame is also larger, obviously, and so in POWERLINK you can have frames as large as 1524 bytes. CANopen is typically a few bytes long. CANopen it's rare to see a CAN application running faster than 2 millisecond cycle times. In POWERLINK you can be running at 100 microseconds or even lower. We even have some examples where people running at 30 microsecond cycle times. But that requires some very specialized hardware. The protocol itself doesn't care, it's just about how you implement that communication. So POWERLINK is maintained by the Ethernet POWERLINK Standardization Group. So this is an open source technology. There is no licensing here, there is no patents. POWERLINK is not a protocol that's for sale. You can get onto the ethernetpowerlink.org website and you can download the specification, or you can go to SourceForge and you can download the stack. So when we're running at very fast cycle times, if you're running a large system, as I showed before, you might have 24 stations or 17 I/O stations, plus a bunch of axes of motion, and you're trying to run at like a 200 microsecond cycle time. That means that you really don't have much time for jitter in the system. So, so from the time you get a pull request until you respond to that pull request, you're looking at a couple of microsecond response time. So that means that you can't have a standard RTOS. You know, if you want to run slow with 3-4 microsecond cycle times, you can use a regular RTOS with a regular microprocessor. You can just download the POWERLINK driver and it just works. But if you're trying to run a high-performance system, then you're going to need some hardware assist to minimize that CPU jitter that you normally get. So there's a bunch of solutions out there that you can use, and here are the companies that provide those solutions. So you can use an Altera or a Xilinx FPGA, and in which case you can download the POWERLINK application for Altera or for Xilinx. Again, it's on the POWERLINK website, and that is free as well. Or you can go to some protocol chips. There are some chips out there that support multiple protocols. So you might have, if you are building a device today and you want to use Profibus and you want to use Ethernet IP and you want to use EtherCAT and you want to use POWERLINK, you can go to Texas Instruments and you can get their Citara chip, or you can go to Hilscher and get their NetX chip, or you can go to Anybus and get you can go to HMS and get their Anybus chip. So there's a whole bunch of variety of hardware out there. And then if you're working with POWERLINK through an operating system interface, it's already running on VxWorks, QNX, Windows, and Linux, so that's all available as well. But again, all this stuff is open source. You can download it, you can port it, you can, nobody owns it. You can grab it, you can, we don't recommend that you change the protocol because then you're not compatible with other POWERLINK devices. So again, it's open source, hosted on SourceForge. Here's the link, but you don't have to remember it. All you have to do is bring up your Google window and Google POWERLINK, and Google just do POWERLINK space SourceForge, and you'll find that link. So some of you may not have heard of POWERLINK before, but it is actually quite a prominent standard worldwide. This is what the picture looks like, and that's based on IMS research from 2013. You have Profinet and Ethernet IP taking about 30% of the market right now, and then you have a significant amount of Modbus out there. But for the real-time applications, you have EtherCAT and POWERLINK running at about 7% and 9%, and then you have a whole bunch of others at around 7%. But what is important to note here is that there aren't too many real-time applications running under Profinet, and there aren't too many real-time applications running under Ethernet IP. So the majority of the real-time market is right here, and that's basically where you see people using EtherCAT and POWERLINK. In China, there is a government standard. It's kind of like an IEEE standard, but it's a Chinese government standard, GB/T. GB on its own means that it's government recognized. GB/T means that it's government recommended. So in 2011, POWERLINK became a GB/T standard, and that's the standard number here. So the Chinese government now recommends POWERLINK for automation, and as a result of that standard now, I think we had something like 23,000 downloads from the POWERLINK website just into China alone over the last year. So it's become a very popular network, and we're seeing a lot of machines today built with POWERLINK. Okay, so I mentioned in the second video that I showed, I mentioned that there is some safety communication going on. So generally people think of safety as a hardwired solution. So if I want to have an emergency stop button, or I want to have a light curtain, or any other safety features, I typically will hardwire things. Well, you can actually have safety sitting on POWERLINK instead. So if I want to add the safe component, all I need to do is put it on the same POWERLINK network, and POWERLINK speaks safety. And then there is a layer on top of POWERLINK called Open Safety. It's an open source standard. It's completely divorced from POWERLINK, but it will run on POWERLINK. And it allows safe communication between two components. So if you're trying to do a TÜV certified machine that you're going to be shipping to Europe, you can grab the Open Safety Stack, which is also maintained by Ethernet POWERLINK, by the Ethernet POWERLINK Standardization Group. And it's already been TÜV certified, so you can just use it. So the idea behind Open Safety is that you're running safety on the same bus that you're using. So You have your standard communication happening, then you have open safety communication, and they both happen on the same bus and they do not interfere with each other. So open safety has been around for a while, since 2008, and again, it's manufacturer independent. So there's a bunch of safety standards out there on the market. You have ProfiSafe running on Profibus and Profinet. You have SIP safety running on Ethernet IP and Circles. You have FSOE running on EtherCAT, and then there's some other standards. But the nice thing about open safety is that it is bus independent, so you can actually run open safety on any of these buses. And what that means is that if I have a manufacturing line built on a bunch of machines, where those machines are built by different machine builders, I could theoretically have a machine that's PowerLink based, Circos based, Modbus based, Ethernet, so I could have all these different machines. I can connect them all to the same network and they will all speak open safety. So that's a very nice way of unifying my safety on my manufacturing line. So open safety today is actually being used by Sidel, by Nestle, and Alstom, and that's also going into their specification when they put out bids. So everything I've talked about so far is available on the Ethernet PowerLink website. There is a publication that's worth downloading called Ethernet Facts. It compares the 5 major technologies for industrial Ethernet, and so I would highly recommend downloading that PDF and reading it. It's right on the website. There's also a LinkedIn group, so you can get on and you can ask questions and you can get connected to people who support the PowerLink technology, etc. And that's pretty much all I have. I'm going to have Carrie now read me some of the questions that some of you typed. Hopefully some of you had some questions that you typed in, and Carrie will read those off to me.
Thanks, Barry. It looks like we do have a couple questions here to answer. The first one is, what is the advantage of direct node-to-node communication?
Okay, so as I mentioned earlier, just going to go back to the beginning of the presentation here. It is really a way of doing synchronization. So, so this is the slide that I used, and I'm just going to go back here and start the slide again. So the idea here is that you can do any 2 components, or any component that puts out a value on the network is going to be seen by everybody else. And that means that I can have one encoder and I can have several motors that synchronize to one encoder. So I was talking to a machine builder the other day that built a large bagging machine. And they have a large timing shaft connecting several gearboxes together, and that's how they did their synchronization to guarantee that everything was running at the same speed. They have a very massive shaft, and that shaft is connected to a bunch of gearboxes, and all those gearboxes are getting synchronized accordingly. Well, you don't, instead of spending thousands of dollars on that kind of a mechanism, you can use PowerLink, and you can use the cross communication, and then you don't need any of that hardware. Next question.
Sure. We just had one submitted. When would you use EtherCAT instead of PowerLink?
Okay. So both EtherCAT and PowerLink are real-time standards, and they're both widely available. EtherCAT is a proprietary standard that is owned by Beckhoff, and it requires licensing. So you have to get your license, you have to get your development environment approved, you have to then do your certification. PowerLink is an open standard. So anything that you can do is with EtherCAT, you can pretty much do with PowerLink. As I showed earlier, there are some cases where if you're in a noisy environment, PowerLink is going to be a much better standard because it is more immune to noise. If you need to do slave-to-slave communication, as I showed you, it's also better to use PowerLink because in EtherCAT, the packet has to go to the master, then back to the the other components that need it. Whereas in POWERLINK, that communication happens directly, so you can do time synchronization much simpler. And lastly, POWERLINK is actually very good on video. So if you're trying to do video or imaging of any kind, that's very slow on EtherCAT, whereas on POWERLINK you can have some, I've seen examples where there were two live video feeds, compress high definition video, and then you have a system running at a 400 microsecond cycle time, and everything runs flawlessly, and the video was jitter free. So it's a much better, if you have a very large system or if you have a lot of data going on that network, then I would use POWERLINK instead. But again, it's an open standard and it's free, and so so there are advantages to using POWERLINK. Next.
Yep, I think you may have just answered this one, but what does it mean that POWERLINK is an open source?
Yeah, so open source basically means that we use the BSD license, which means that you can grab the code and you can do anything you want with it. You don't have to sign any terms and conditions. Nobody owns the code. You can take the stack and do whatever you want with it. You can use it. You can distribute it. It is freely available. So so there are no restrictions at all of any kind. It's pretty much like the way Linux is, except Linux is sometimes GPL, whereas so anyway, the point is that it's a BSD license. You don't have to worry about any of those legal issues.
Okay, and our last question is, how fast can the cycle time be?
Yeah, so as I mentioned before, you can run POWERLINK, down to 100 microseconds, and we've seen some specialized hardware people are running. This was actually in China. We have some machine builders running at 30 microseconds. I have no idea what they're doing with 30 microsecond cycle times, but they're doing it. But I've never seen any real examples where the architecture made sense to run that fast. But POWERLINK runs really fast, and because you're running on standard Ethernet, as industrial networking evolves, today industrial networks run at 100 megabits. As we get to the gigabit speeds, POWERLINK will just work. So that kind of answers it. But what I would suggest is if there are any additional questions, feel free to send me an email or feel free to call me. Here's my contact information on the screen. And I'd be happy to answer or discuss or help or whatever. Basically, the Ethernet POWERLINK standardization group is here to help people adopt using Ethernet POWERLINK. We don't sell you anything. We're not selling licenses. We're not selling products. We're just a standardization group that is maintained by our members. So, so if you need help, we'll connect you with the right people. If you have questions, we'll answer them. If you're looking for POWERLINK components, we can point you in the right direction.
Okay, thanks again, Sari.
Thank you
to all of the participants today. And I want to thank our sponsor, B&R Automation. Just as another reminder, this webinar has been recorded, and an email with a link to the recording will be sent to you in the next 24 hours. If you have any additional questions, as Sari said, please just feel free to email him or myself, and I'm happy to pass along any questions. Be sure to visit www.motioncontrolonline.org for a list of our upcoming webinars. Our next webinar is Wednesday, October 15th, and that'll be on maintenance and what you can do to make your machine last longer. Thank you, everyone, and have a great day.